When someone asks, "How much does PFAS testing cost?" it sounds like a simple pricing question. But in reality, that question opens up a much deeper discussion about analytical chemistry, regulatory compliance, environmental liability, and advanced instrumentation. PFAS testing is not just a lab service. It's a scientific process designed to detect ultra-trace contaminants that can impact public health and long-term environmental safety. In this video, I'll walk you through what truly drives PFAS testing cost, from sample type and detection limits to regulatory methods and analytical technology, so you understand not just the price, but the value behind it. PFAS, often called forever chemicals, are per- and polyfluoroalkyl substances known for their extremely strong carbon-fluorine bonds. That bond strength is why they resist degradation in soil, groundwater, and biological systems. Once released into the environment, they persist for decades and can travel long distances through water systems. From a public health perspective, PFAS are concerning because they bioaccumulate, meaning they build up in living organisms over time. Studies have linked certain PFAS compounds to cancer risks, immune dysfunction, liver toxicity, and developmental issues. Detecting them at ultra-low concentrations requires specialized, validated analytical methods, and that complexity directly impacts testing cost. The first major cost driver is the sample matrix. Testing drinking water is very different from testing soil, wastewater, air, or blood serum. Soil requires extraction steps. Biological samples require protein removal and cleanup. And each additional preparation step increases labor time, consumables, and complexity. Other factors include the number of compounds tested, the detection limits required, turnaround time, and sample volume. Ultra-low regulatory limits demand highly sensitive instrumentation, while rush analysis requires priority scheduling and expedited QA review. Larger projects may reduce per-sample costs, but urgent or small batch testing typically costs more. The gold standard for PFAS analysis is LCMS/MS. Liquid chromatography coupled with tandem mass spectrometry. This technique offers high sensitivity and selectivity, allowing laboratories to detect PFAS at parts per trillion levels while distinguishing them from background contamination and matrix interference. However, the instrumentation is only part of the story. Sample preparation methods like solid phase extraction, SPE, and advanced filtration are critical for concentrating analytes and removing interference. These steps require validated protocols, specialized consumables, and trained analysts, all of which contribute to overall testing cost. Targeted analysis focuses on a predefined list of known PFAS compounds. It is faster, more cost-effective, and ideal when regulations specify exactly which compounds must be measured. However, once analysis is complete, you cannot retrospectively search for additional analytes outside that list. Non-targeted analysis, often performed using high-resolution mass spectrometry, allows laboratories to detect both known and unknown PFAS compounds. The data can be stored and reanalyzed later as regulations evolve. While this approach is more expensive, it offers strategic long-term value by reducing future regulatory risk. Different environmental media require different regulatory methods. Drinking water testing follows specific EPA methods such as 537.1 or 533, while wastewater, soil, and biosolids may follow method 1633. Air emissions are analyzed using separate protocols like OTM45 or OTM50. Each method defines strict requirements for calibration, recovery, blanks, isotope dilution standards, and quality control acceptance criteria, Compliance with these standards ensures defensible data during audits or regulatory inspections, and maintaining that level of compliance adds to the overall analytical cost. Drinking water basic panels typically range from $100 to $250 per sample, depending on the number of analytes and detection limits. Soil samples generally cost more, around $200 to $550, due to additional extraction and cleanup procedures. Biological samples such as serum testing can range from $600 to $900 because of extensive preparation and validation requirements. Extended PFAS panels and rush turnaround requests add additional costs, reflecting the increased instrument time, standards, and expedited quality review. In PFAS testing, data defensibility is everything. Laboratories must use validated methods, perform regular instrument calibration with certified reference materials, and participate in third-party proficiency testing to demonstrate accuracy and reproducibility. Chain of custody documentation ensures sample integrity from collection through reporting. Without strong quality assurance systems, even accurate analytical results can be challenged, which is why reputable laboratories invest heavily in compliance infrastructure. Consider a municipal water authority facing new regulatory limits for PFOA and PFOS. They required ultra-low detection limits in a complex drinking water matrix with an urgent turnaround timeline to maintain compliance and public trust. Using optimized LC-MS/MS methods and advanced extraction techniques, compliant results were delivered within 5 days. This case highlights how investing in precise PFAS testing can prevent regulatory penalties, protect public health, and reduce long-term financial risk. When evaluating PFAS testing providers, pricing should not be the only consideration. Instrument capability, regulatory expertise, method validation experience, and data reproducibility are equally important factors. A specialized laboratory with advanced instrumentation and experienced scientists becomes more than a testing facility. It becomes a strategic partner in environmental compliance and risk management. Because PFAS testing isn't just about cost, it's about confidence in your data,